Hello everyone, my name is Gmeiner. I work at the Galia's graphics team, and today I have the pleasure to talk about the new backend compiler for etnaviv. Here is a quick overview what I'll be covering in today's presentation. First, we will start with the motivation behind the project, why I started it and what problems I'm aiming to solve. Next, I will talk about the status quo, when the project started. After that, I will introduce the target instruction set architecture. We will then move on to the road to success and look at the progress I have made, the milestones achieved, and how the project has evolved over the past few weeks. Following that, I will share some shader debugging techniques I've been using, which have been crucial to track down issues and validating the implementation. I will then outline some of the challenges I've faced during development and how I overcome them. Finally, I will wrap up with further work, discussing what's next for the project and the remaining areas that need to be improved. Let's get started. Motivation. The current compiler, or let's call it near translator for etnaviv, is less than optimal regarding its architecture. It uses near for register allocation, breaks near validation, is hard to follow, and takes too much of my time when a bigger near refactoring is happening. For me, it's not that fun to work with. I want a grown-up compiler. There are many ready-to-use near passes that are a lot easier to work with if there is a backend IA and a real backend compiler. Sure, it might be possible to do the same with the current, but that needs a lot of duct tape. I think in the long run, memory-safe programming languages will become more and more important through the whole graphics stack. Rust is just one of them. As Mesa gains more and more components that are written in Rust, I think following that trend is a good thing. Rust helps to write efficient and safe code. Everybody hopefully knows this. For me as a developer, Rust offers some other really nice benefits. There is no need for an external unit testing framework like Gtest. Another heavily discussed topic is code style. Rust FMT makes my life a lot easier as I really do not need to care about code style at all. I write my code and let Rust FMT do its magic. Let's have a look at the initial situation. First, there are a lot of good resources for learning about compilers and compilers in Mesa. Many talks and blog posts show how to write a good compiler and how to use it for OpenGL and Vulkan. I recommend visiting planetfreedesktop.org and the XDC YouTube channel. You find a lot of helpful content from the community. At last year's XDC, I already talked about the new backend compiler for etnaviv. Looking back, it was a good first step, but was stalled by some missing ESA spec bits. The good news is I can reuse many of the near passes I wrote back then, so not much time was wasted. As I always wanted to have a good foundation to build a compiler on top, I needed much more unit testing. I wanted to take a random but meaningful encoded instruction from the binary blob, disassemble it, compare the result with the expected string, and be able to take that text representation, assemble it, and compare it with the initial test data. This gives me the confidence that ESA spec is complete enough. As a waste product, there is assembler CLI that can be used when somebody wants to replace shader binaries, for instance. The best part about the new assembler lib is that it is written in Rust. It uses the PES library for parsing and procedural macros to work directly with the ESA-spec XML file. It makes it easy to add new instructions or bits by simply updating the XML file. When I was working on the proof of concept compiler, I spoke to some Mesa driver maintainers to see which programming language they preferred for a new compiler. Most suggested modern C++ or Rust over C. At that time, the NEAR project was still in its early days. Now, after several months, NAC has made a lot of progress and done all the hard work of proving Rust can be used for backend compilers in Mesa. But there is no shared Rust code for compilers. This isn't a problem, but it means that someone might want to work on that topic. As a refresher, let's talk about the target ESA of Vivanti GPUs. My target instruction set architecture uses a fixed size of 128 bits for each instruction. It supports up to 3 source operands. The ESA is a VEC4 based one. There are 3 different encodings: the default encoding, the extended instruction encoding, and the enhanced vision instruction set. We have 2 types of registers: temporary registers and uniform registers. Temporary registers are used for general operations, while uniform registers are more static, storing values that don't change during shader execution. Some temporary registers might contain fixed input or output data semantics. It also supports inline immediate values, which means we can put small constant values directly into the encoded instruction. As I told you, all of this is defined in etnaviv.xml file using ESA-spec. Let's have a look at the sample instruction from the target instruction set architecture. This instruction was randomly chosen, but it shows a lot of features I talked about. First, it uses 3 different types of source operands: a temporary register, T0, an immediate value, 32, and a uniform register, U0. It is also using the U32 instruction type, meaning it's working with 32-bit unsigned integers. Let's talk about how I got started with this project. While working on the assembler, I really enjoyed using Rust, so I decided to try building another Rust-based compiler. I came up with my master plan: reuse the near passes from my previous proof of concept backend compiler and take all the reusable parts from NAC. The goal was to write enough code to be able to compile a very simple shader. Getting it to run on the actual GPU would be a challenge for later. I decided to target OpenCL because it was very little state to worry about, supports many arithmetic instructions and data types. This way I could just focus on the compiler itself. By lowering operations in NEAR, I can take advantage of NEAR's optimizers, which do all the hard work for me, and I do not repeat the same optimizers in my backend compiler. NEAR is also so flexible that it allows hardware-specific instrings and makes the life really easy for a compiler developer. After translating from near to the backend IR, there's usually some extra cleanup to do. That's why I wanted to include some basic optimizations from the start, like copy propagation and dead code elimination. By the way, these are the only optimization passes I currently have written in Rust. With this, I can transform near already quite well to fit my target ESA. Supporting control flow like loops and conditionals was a priority from the beginning. Fortunately, I could reuse Nux's generic control flow graph implementation, which saved me a lot of time in testing. Also, it's important to support all the hardware bit sizes from the start. Choosing OpenCL helped here a lot. The etnaviv backend compiler, or shortly EBC, started about 3 to 4 months ago. This time I'm focusing on building it with a strong foundation and a long-term vision. Instead of rushing to get quick results, I want to ensure that the architecture is solid and flexible enough for future extensions. Let's have a quick look at the past month of work. My biggest wish was to keep it a secret as long as I could. It is another proof of concept which might never enter the final stage and will never be merged into Mesa. So, I started again as a fork of the NUC compiler. As the target instruction set architectures are different, I had to make it VEC4 ready and have done many rounds of refactorings. I think I had at least 2 versions of ir.rs before I settled with the kernel one. I do not remember the time it needed to get to the point where I was able to compile a simple OpenCL shader into something that looked okay-ish, but it was less than a week. I had no liveness analysis nor a real register allocator, and that should be the case until quite late in the development process. Lucky me, there are 64 temporary registers I could reuse. In the second stage of development, over the past few weeks, I was focused on refactoring and fixing bugs. During this period, the compiler was able to pass around 200 to 300 piglet tests. It was a small but promising milestone that showed things were moving into the right direction. I also started discussing the proof of concept with Faith. At this point, the source compiler Rust directory was born. Faith and me moved the following components into this new folder. We have now an slice trait, a bitset struct, the control flow graph builder struct, everything to work with near shaders in an immutable way, and a small vec struct. I hope that the memstream layer and the near instruction printing also find its way into common code. I also began having conversations with Carol about OpenCL topics. This helped me identifying some OpenCL specific challenges that the compiler still needs to address. Even though there was progress, I still was uncertain about the proof of concept's future. In the next phase, the number of passing piglet tests started to increase, although progress was slow and required a lot of effort. I managed to reach around 1000 passing tests, but it came with a lot of frustration. Debugging shaders took up most of my time during this period. Despite the difficulties, I continued fixing bugs and adding more unit tests, which eventually increased the number of passing tests to more than 2500. A major turning point was adding support for liveness analysis and register allocation. With these additions, the number of passing piglet tests increased to around 3000, showing that the compiler was becoming more robust and capable. Also, at this time, I started to test the OpenCL CTS suite, and I was surprised how much I was pathing at that time. So, to summarize my road to success, when we look at how I started and how it is going, I would say the compiler architecture I've chosen works. The optimization path is doing a good job, and all the near lowerings looking fine too. There's still room for improvement for the generated assembly, and there are also still some failing tests, mostly that have problems with the precision of the results. But overall, I'm really happy how this ended, or how the current state is. Let's dive into some of the techniques I used for debugging shaders during the development process. The more tests started passing, the bigger and more complex the shaders became, making it harder to debug issues. Thankfully, if a compiler supports atomics and basic control flow, we can use printf debugging in OpenCL. This works right off the box and it was really helpful. With printf, I could validate that my load instruction were fetching the correct data. It also allowed me to split complex one-liners into multiple steps and check the intermediate results. But at some point, even printf debugging wasn't enough. This is because a single OpenCL instruction can end up generating several GPU instructions, making it hard to track down issues. One of the most important things for me was to understand the flow of data in the shader. I wanted to see the values in the destination registers after each GPU instruction. Since I have a lot of registers available, I thought there must be a way to achieve this. My idea was to re-index all the relevant registers in the backend IR and then add store instruction to every used register and its vector components. This approach allowed me to track how data moved through each step of the shader. It opened up a whole new world of debugging for me. Let's have a look at a simple example to see how this technique works. This is a very simple OpenCL shader example that uses the native square root function in OpenCL. I have chosen the native square root function as it maps directly to Near's FSQRT ALO opcode and is better for presenting on the slides. To make sure this debugging technique works properly, we need to ensure that the global size is set to 1. When we enable this special data flow mechanism, it generates shaders looking like this. This shader includes all the extra store instructions for each register and its components. It stores all the data into a special buffer object. After running the OpenCL kernel, we can map and read the buffer object to check the values of the registers and see how the data moved through the shader. When we put all the information onto one slide, we clearly can see the flow of data. In this example, we have an input of 4 and we get the output of 2 for this square root function. This was just a simple shader to show how the debug mechanism works. I have used this technique successfully on much larger shaders. It might not be a new idea and could have been used by others, but I haven't seen anything like it in Mesa's code base, and it saved me many hours comparing to do it manually. As this debug mechanism is not that much code, I am playing with the idea to just ship it, because I think somebody else might run into some issues and might want to stare at the data flow. Let's talk about some challenges I faced during development. During prototyping and the whole development process, I was running into many challenges. First, having two different compilers for one driver seemed manageable at first, but in practice it turned out to be quite tricky. I had to duplicate a lot of code, especially for emitting uniforms in the command stream. When I added OpenCL image support, I ended in a ublitter call and needed a compiler too. One thing that took some time in my head was the fact that near is untyped and my instructions are typed. Even my inline immediate values have types. First, when I was confronted with this challenge, I started to reconsider some life decisions and took a short break from this whole proof of concept compiler topic. After some days, I came up with crazy ideas how to improve the situation and created some merge requests that luckily never got merged. The feedback I got for these merge requests helped me to deal with my problems, and in the end it worked out. Lastly, I underestimated the amount of reverse engineering still needed. I had to identify new instructions and figure out the extended instruction encoding. Some issues like understanding a single bit in the load instruction took me several days to solve. I found that examining how the same feature behaves in different GPU generations can be helpful, but it is a slow process. There is still more reverse engineering to do, and I will need to keep refining the ESA model in ESA spec along the way. Besides getting EBC reviewed and merged in its current state, there are a few areas that still need further work. In C, integer promotions refer to a set of rules that define how smaller integer types like char, short, are converted to larger integer types, typically int or unsigned int, during arithmetic operations. The purpose of these promotions is to ensure that the operations are performed using at least the width of the int type, which is usually native word size of the machine, to avoid inefficiencies and unexpected behavior due to type sizes. You might wonder why this topic is relevant in this context. As I want to write a competitive compiler compared to the binary blob, I often compared the assembly of both compilers and came across this topic. You might remember that my target ESA is typed, and almost all other instructions are supporting 8, 16 and 32 bits wide data. I think it's time to look at a small example. Here we can see a simple kernel that adds two char values. On the bottom we see the near representation, or a part of the representation of the shader. And we can also see that we are doing 3 conversions. 2 are going from 8-bit to 32-bit, and 1 is going from 32-bit to 8-bit. And these kind of conversions are not needed, and the binary blob compiler do not emit them. It just works directly on the 8-bit data type for this example. So there's still room of improvement here. If I want to get the EBC compiler into the ballpark of the binary compiler, I think the easiest way would be to have OpenCL only a near pass that removes all these not needed type conversions. But it's still on my to-do list. I have a proof of concept, tested it a little bit. I even talked to Carol about the idea, and he is in the same boat as me, and it might even help other backend compilers in Mesa targeting OpenCL. There are several things I'm planning to work on moving forward to expand the capabilities of the compiler. First, I want to extend the usage of the compiler to handle more shader stages. Right now, it's focused on OpenCL, but the goal is to cover all shader stages. From the experience with the old compiler, this task shouldn't take too much time. And I think this will be one of the first tasks I want to work on after EBC landed. Next, I want to support more GPU generations. The compiler is written with all GPU generations in mind, but it was never tested, and a legalization pass is missing. I am currently targeting 1 GPU generation for all my work, and it still needs some testing and validation to support the older GPU generations of Vivanti GPUs. And the major long-term goal is to fully replace the old compiler. Right now, both compilers are being used together. Remember OpenCL image support, and that complicates things a lot. Once the new compiler is ready, I plan to phase out the old one, but it will take some time and some Mesa release cycles to get to that point. Another area I'm exploring is building an instruction stress tester like the one from NAC. In etnaviv, we have an instruction opcode verifier written in C that lives in the etnaviv GitHub repository. And I really would love to move this code into Mesa's codebase, convert it to Rust, as the compiler is written in Rust, and it should help me to even have more trust in the things we are doing in the compiler and the whole ESA spec definition of the instruction set architecture. So, thanks for watching my talk. I hope I could give you a little insight in the development of the etnaviv backend compiler. I will create the merge requests for EBC during XDC, and I hope everyone is curious to have a look at it and do code reviews and help me to get this piece of work faster into Mesa than usual. With that, I also want to thank everyone I talked about Rust, near OpenCL, and guided me into the right direction. And thanks for allowing me to ask all these stupid questions. And Carol, sorry if I always come with the same problem. Hey, the binary blob compiler does this. Why we aren't doing this? Why is our near so big? So thanks for your time, for your support. And with that, I think I'm good in time. And it's now time for your questions. Oh, and by the way, if you like to work on these kind of topics, maybe Igalia is the right place for you. So, let's start with the questions.